Hello, my name is Alec Reed, and I will be presenting the system my co-authors and I have designed to generate control-Lyapunov functions and extract controls. Here's an image of our overall generation and extraction framework, but first, let's focus on just the CLF learning loop. To start, we generate state control samples by sampling possible states in our defined region and calculating associated controls. These samples are passed to our feed-forward neural network that will become our CLF. After some number of training steps, the network is passed to the verifier. During verification, automated theorem proving is used to check if our network indeed acts as a CLF. If the verifier finds states for which Lyapunov conditions are violated, these states are appended to the list of samples and the network retrains. This loop is repeated until the network is verified to meet the Lyapunov conditions. After verification, we can use that CLF as a means of vehicle control. We show that we can eliminate the need for hybrid controllers by calculating the maximum curvature for which the CLF is valid. This allows construction of complex paths and execution of controls with verified control guarantees. Thank you, and please swing by our poster for further discussion.
So imagine I'm a robot. First, I scan the environment, obtain a point cloud, then I move around the room, and then return to a similar place, but with a different angle. I obtain another point cloud. Now I have 2 point clouds with transformation changes. How could I identify these 2 other similar places? So my work is to learn point cloud features that is invariant to transformation, and then use that to do place recognition task. As you can see, the left top, the point cloud is rotated and translated, and then our learned features are remain similar, and then other descriptors methods, they will change. So if you are interested, welcome to come to my poster session. Thank you.
So the ability to learn from human evaluation and human guidance is quite important for robot learning. However, human guidance is quite expensive, calling for the method to be more sample efficient. So we hypothesize that the learning can be more efficient if we can equip the robot with a representation that is better aligned with a human representation. So in this work, we propose a dual representation for learning with human guidance. The robot agent will first use a low-level fine-grained state and action space for learning continuous control, while at the same time, it will keep a symbolic scene graph at like a high-level representation of human internal states. And with this architecture, the robot can actively and efficiently query human trainers for guidance during the training process. In 5 continuous control tasks, including a real-world manipulation, we demonstrate that our algorithm could achieve much better sample efficiency and user experience. So if you're interested, feel free to check out in the poster session. Thank you.
Hi, I'm Gilbert. I'm here to present generalized locomotion controllers for quadrupedal robots. Recent years have seen the emergence of a growing catalog of quadrupedal robots seen in both industry and research. And these quadrupeds are seemingly converging towards similar body plans. This leads one to wonder if it's possible to develop a single general locomotion controller for all of these robots. In this work, we present a learning-based framework that explores a setting where the embodiment of the robot can vary. Our system randomizes the morphological parameters over a diverse set of robots, reducing the need for robot-specific information during training. As a result, our policies generalize well, and they transfer directly to a wide set of robots. And you can download our policies as pre-trained baselines without any further fine-tuning. They can be deployed on newly developed quadrupedal robots. Yeah, so if this sounds interesting at all, please come check out our poster. Thank you.
Hi, I'm Kylian Yu, and in this work, we focus on finding a time-optimal trajectory for quadrupedal vehicle that pass through a given set of waypoints. This problem is challenging since the optimal solution is located on the edge of visibility constraint, which is unknown and hard to model explicitly. In this work, we used a sequence-to-sequence model to generate an optimal trajectory, and to train this model efficiently, we utilized the Bayesian optimization method from our previous work that deal with this unknown constraint. So we first find the optimal solution for a subset of training data set and overfit our neural network model to that subset. And then we utilize the reinforcement learning to generalize the model to entire data set. As a result, our model can generate the trajectory that is up to 20% faster than the one from the baseline method. And if you're interested, feel free to find me in the poster session and also check the QR code for the video. Thank you.
What would your robot need to help you fetch the rapid test behind the Harry Potter book? Well, it would need to identify the Harry Potter book, something that Clip can help with. However, it would also need to understand what behind means in 3D space, something that learning from 2D internet image caption pairs just doesn't teach you. In this project, Semantic Abstraction, we ask, how can we give Clip new 3D understanding capabilities without hurting its robustness? To do this, we use Clip relevancy maps, which highlights where Clip thinks an object is in the scene. By learning 3D completion and localization on top of the relevancy maps, our approach generalizes to any object category that Clip generalizes to. Come to find out more at the poster session and play with the demo. Thank you.
We aim to build a system for scooping widely varied foods for downstream tasks such as assisted feeding and cooking. We leverage a second arm to stabilize the food position during scooping to prevent the need to chase foods around a plate. However, the addition of a second arm can lead breakage failures when the two arms squeeze the food item together, causing it to fracture or deform. To tackle this problem, we introduce a bimanual scooping primitive with 3 phases: pushing, scooping, and transfer, and 3 stabilizing strategies: angled pusher, cupping, and pinning. However, using this primitive can still lead to breakage failures with fragile foods like tofu. So we learn a risk classifier to identify these fragile food settings, and then we use a failure classifier to servo and adapt our cupping strategy to terminate early when a breakage imminent state is detected. Our method is able to successfully scoop 87.1% of robust foods using these 3 stabilizing strategies and prevent food breakage in 16.7% of cases for fragile foods. Thank you.
Can we skip to the next slide, please?
I'm Justin, and I'm here to present our work on last mile embodied visual navigation. We find that prior work in visual navigation has trouble reaching the goal, even when the agent sees it. To fix this, we propose Sling. Across simulated and real-world scenes, we connect Sling to previous visual navigation research via simple geometric switches. This allows us to explore the environment with previous visual navigation research and perform last mile navigation with Sling. Our results across modular, self-supervised, and reinforcement learning baselines show that Sling improves performance, and these results are also consistent across data sets. We transfer these results to the real world, where we demonstrate Sling across 120 trajectories over 3 test scenes. If you're interested in robot navigation, embodied agents, or sim-to-real transfer, please say hello. Our paper ID is 64. Thank you.
Hi, today I want to talk about how robots can be more transparent to help humans teach them better. A while back, I collected some demonstrations to teach an imitation policy, and with my data, the policy was 14% successful. So I asked my friend Sid to give me more demonstrations. Sid was equally successful, as you can see on the right, but when I added Sid's data, the performance of the policy went down, and this was quite surprising. Why is the policy worse with even more data? This is really a tale of 2 measures, novelty and likelihood. When I plot my data in orange, it is fairly aligned with the base policy, but when I look at Sid's data, it has a lot more unlikely data in familiar states. Our idea is to filter this data out, and more importantly, guide Sid to give more consistent demonstrations. Our interface actively elicits better demonstrations and leads to significant improvements over naive data collection methods. If this intrigues you, I'd love to chat with you at our poster. Thank you.
Good morning, everybody that is already here. So in our work, we have been looking into combining deep reinforcement learning with episode-based reinforcement learning. So why are we doing that? Essentially, the idea is we get the smooth control capabilities and at the same time also energy efficient solutions. And our method also naturally scales to non-Markovian rewards and also sparse rewards quite naturally. On top of that, we achieve an exploration that is directly in the whole trajectory space, not on the individual state space where we ultimately want to act in. From the method point of view, we essentially use a trust region-based method that is optimizing a policy in a trajectory parameterization space instead of the raw action space. In our experiments, we tested a quite large set of benchmarks, including the whole meta world benchmark set, as well as some more challenging control tasks you can also see up here. If you're interested, join my poster sessions and have a talk. Thanks.
Hindsight experience replay is a well-established sample-efficient method for doing goal-conditioned reinforcement learning. However, it can come with a pretty significant downside, which is that it's actually asymptotically biased in stochastic environments. In particular, we find that HER has a tendency to be actively risk-seeking when there is significant stochasticity in an environment. We have two main contributions. First, we show a mathematical analysis of HER and its bias, and are able to show under what conditions HER's bias is likely to significantly influence the value function. And second, we provide a way of correcting for this bias without affecting HER's native sample efficiency at all. We test this on a wide range of stochastic robotics environments and find that Usher significantly outperforms HER on these environments. Thank you.
Hello, everyone. My name is Mariah Schrum. In our work, we investigate the problem of learning from suboptimal and heterogeneous demonstrators in a robot-centric learning from demonstration paradigm. Prior work has investigated how to learn from suboptimal demonstrators by learning to map these suboptimal demonstrations to better demonstrations. The issue with these works is that the demonstrator never actually learns how to become a better demonstrator. To solve this problem, we introduce what we call reciprocal MyMeld. Reciprocal MyMeld learns a personalized embedding that describes the way in which a demonstrator is suboptimal and then uses this information to provide actionable and informative robotic feedback to the demonstrator to improve upon the quality of their demonstrations. Across 3 human subject studies, we show that our approach results in higher quality demonstrations as well as better learning outcomes for the agent. For more details, please see us at the poster session.
Good morning. My name is Mark van der Merwe. I'm presenting our work learning the dynamics of compliant tool environment interaction for visio-tactile contact servoing. The goal of this project is to control the extrinsic contact between a compliant tool and its environment for tasks such as robotic scraping. The challenges of controlling this extrinsic contact include the complex deformations of the tool, as well as the contact dynamics. Additionally, we do not assume access to object or environment models, and so we must rely upon noisy and partial multimodal sensing. In this work, we propose to directly represent the contact state between the tool and environment as the features of interest in the system and learn how they evolve from multimodal inputs. We can then plan to realize desired contacts in our environment. In our experiments, we show we can servo desired contact trajectories, as well as generalize to a new tool and new environment. Thank you.
Hi, I'm Matt. I'm presenting our work which enables mobile robots to carry out single episode missions in environments with uncertain dynamics. For example, this mobile robot wants to get somewhere in a nuclear reactor room to carry out a survey, but there's an uncertain radiation level distribution which cumulatively damages it.
And in each single mission, it encounters a unique radiation level distribution. So it's not feasible to pre-generate a policy. And it also has to make the most of the very limited number of radiation level measurements that it can collect online. We maintain a belief about the environment's dynamics using Gaussian processes. And we make use of methods from Bayesian model-based reinforcement learning to act much more effectively in these kind of GP modeled environments than previous methods are able to. And one interesting thing that you see in the results is due to the online setting, it's actually possible that taking time to come up with better policies can lead to you getting exposed to more cost, which is a bit of an interesting aspect.
Hello, everyone. This is Ninad here. Today, I'll be presenting our work Neural Graphs, which is about learning joint representations for multiple graphs from different grippers. So basically, the aim of this work is to learn a representation which is easy to, which makes it easy to transfer graphs across grippers with different kinematics. So we try to formulate it as an implicit shape representation problem where each graph gets mapped to a vector in a shared latent space. And we try to use, since there is no notion of graph similarity between different grippers, so we try to use object-centric contact maps as a way to guide this notion, and so that the distances between the latent space are meaningful for graph transfer. I would be happy to talk about additional details, and please feel free to visit my poster in room number 40. Thank you.
Hi, everyone. My name is Carl. I will be presenting our work PASTA, planning with spatial temporal abstraction from point clouds for deformable object manipulation. We consider a challenging scenario, specifically given a set of demonstration skills in high dimensional space, such as point clouds. We would like to compose those skills for long horizon tasks and generalize to scenes with more entities. Our method PASTA consists of 3 steps on the high level. We first learn short horizon skills from the demonstrations. And then we learn spatial temporal abstractions to chain the learned skills together. At the end, we perform latent space planning with skilled abstractions to obtain the sub-goals for executions. The sub-goals should be right here. PASTA can solve 6-step manipulation tasks with up to 3 entities in the scene when it is only trained on 1 entities in the scene and primitive skills. So if you're curious about our work, please come to our poster sessions for questions. Thank you.
Hello, everybody. Hope everybody's enjoying New Zealand. Yeah, remember to put on some sunscreen. I got very sunburned. I'm Yen-Chen Lin from MIT, and I'm very interested in building robust robotic manipulation system that can handle reflective or transparent objects, as you guys can see here in our demo on the top. And to do it, our work proposed to use neural radiance field as a scene representation. So here you can see that we're building a scene representation in a few seconds. And then we'll use NERF to synthesize a lot of views to look at the scene from different angles. And then we'll send these views into a pixel-wise affordance model to tell us which 6-degree freedom action to perform. So our work generalized previous excellent work, such as transporter networks, by removing the assumption of depth camera and also extend the action space to 6-degree freedom. So if you're interested in our work, come hang out with me at my poster session. Thank you very much.
Hi, everyone. Today, I'm presenting our work on learning semantics-aware locomotion skills from human demonstrations. I'm pretty sure you have seen a lot of Lego robots walking around the conference venue over the past few days. But if you want to take the robot out to off-road terrains, its perception system needs to be augmented. More specifically, it would benefit if the robot could understand environment semantics, that is the terrain type and the contact properties, in addition to standard geometric cues like terrain inclination or obstacle locations. In this work, we present a way for our robot to adjust the speed and gait of the robot based on the perceived semantics from RGB camera mounted on the front of the robot. Using our framework, the robot can decide the speed and gait automatically based on perceived semantics. And so far, it has worked in off-road terrains for over 6 kilometers without failure. For more information, please come to our poster, and our paper number is ID 470. Thanks.
All right, that's it for the poster spotlights. The poster sessions go on now until 9:50 or 10:50. That'd be short.